So I'll spend a little bit of time talking about some very important representations. So much of our data is represented in a hierarchical format. And so graphs and trees are very often one of the most common ways that we represent data. So I think it's valuable for us to talk just briefly about some of the different options that we have for thinking about representing graph and tree data. So the most common way that we represent data in a graph format, in a tree, is something that we call a node link diagram. And a node link diagram really takes each different node that has children and represents the children at an indented way. So in this particular node link diagram, the root of the tree is all the way to the left, and each of the different leaves are shown at the second column and then the third column, and far right you'll see all the different leaves. Well, one of the most common things I think I'm asked is, how do I squeeze more data into my tree? Well, one of the ways is by, rather than using a single hierarchy and making it flat, what we can do here is have a radial layout. And this radial layout allows the same amount of data, a significantly higher amount of data to be presented, and it's shown in a way that all of it can be visible at once. And this idea of the node link diagram can also be used in this idea that here called thread arcs, that are used to show networks that occur over time. And so you can show a single node and the way that its children propagate. This is very interesting here in thread arc. The idea is that this particular representation is used to show the way that a particular conversational threads are propagating. You could see, for example, on the conversation in the middle on the left that an original conversation is started, and then without comment, another one, and then another one, and another one, and then finally someone comments on the very last one. Whereas if you look at, for example, the one on the top right, the original comment then spawns 1, 2, 3, 4, 5 comments, and then the second comment has a child unto itself. Separately, if you're interested in showing not just the relationships. So the things that these graphs are excellent at showing is the hierarchical relationship. But sometimes the relationship does not just include one of containment, but it also includes one of magnitude. So for this particular kind of diagram, something here called a tree map can become very useful. So a tree map is also a hierarchical diagram like the tree, but each child node is organized according to the area. So you can see here in the top left, that's a node with no children. Whereas go one below it, that node has 3 children, and the one on the bottom has a magnitude far greater than the 2 above it. So something like this is occasionally used. You might have seen something like this, for example, on a disk defragmenting program. Another way that networks are often shown is something here called a chord diagram. And this chord diagram allows you to actually show relationships and magnitude. And so this one would work by mousing over one of the particular edges, which are shown on the outside. And the relationships are shown by arcs connecting each of the nodes, and the width of the arc is proportional to the magnitude, the weight of the connection. And so you can see here, this particular diagram shows a hierarchy and magnitude at the same time. Another way that you might care to show something like this is something called the Sankey diagram. Now, the Sankey diagram is designed to show the magnitude and flow through a network at the same time. So this particular diagram shows how energy is produced and consumed in the UK. So what you can see, for example, is on top, nuclear is the principal producer of electricity in the UK. And if you go and you can see that about halfway down, there's a bar that represents a node where thermal generation is then used. And that is the consumer of nuclear power. And that is then passed on to the right to downstream consumers. So what you can do is you can see how, for example, things like oil imports and oil reserves on the bottom left are then passed into liquid form to various refineries. And you can see the magnitude of the bar here is, the height of the bar represents the magnitude of the relationship. So you can see that there's a number of ways that one could take the same data that is included in a graph structure and choose to highlight hierarchy, time, and magnitude. And depending on how you would choose to differently represent them, if you want to show hierarchy and magnitude, then the tree map is for you. If you want to show time and hierarchy, then think about a thread arc. If you want to show a deep number of hierarchical relationships, then think about the node link diagram. And if you're interested in showing hierarchy and magnitude, think about the chord diagram. And if you're interested in showing magnitude and time, then think about a Sankey diagram. But each of these different methods allows you to take some of the different dimensions of data and bring them to the forefront. So let's connect this back to some of the things that we discussed previously. So something like a tree map, right? A tree map takes, so what are the most visible elements in the tree map? Area. In the tree map, the magnitude of the leaf is proportional to the area that it contains, that it encloses. And if you think back to our a few chapters ago where we described what are the most salient features to human perception when it comes to identifying differences. It's area, right? It was it was a location and area. So by choosing to represent magnitude in area, the tree map is making that magnitude the most salient feature. Whereas if you look at how magnitude is represented in the chord diagram, it's actually a secondary feature to layout. And what you can see is each of the nodes on the edge, the size of the node, and its relative location to nodes next to it demonstrate those are the more salient features. So the things that stand out in this graph the most are the edges around the outside and the relationships that are drawn between them. The Sankey diagram does the same thing for relationship, and it's encoding time. And it's giving time, in this particular example, to the x-axis. So when we look at this and we say, why is time so salient? It's because they've taken position, the x-axis, and turned it into one of the most meaningful features of the graph itself. So if you're thinking about how do I choose which of the following types of representation to use for my own data, you can think about what are the particular dimensions that have the most importance, and then which of these different encodings bring out those dimensions. And that's one of the ways that you will end up looking for the ways that the most important parts of your data become the most perceptible.